So this video is about making an analog cymbal circuit for a drum machine. And the cymbal is one of the most complicated ones. And to hear what it sounds like, sounds pretty good. And we got the sound just the way we want it. It's kind of based on a Boss DR110 drum machine. It's got a gate to trigger converter. So I'm going to show you how to make it. Keep watching the video if you're interested. The essence of creating the cymbal sound is you need to create a set of oscillators, 4 of them to be exact, at different precise frequencies. And so to do that, we use a CD40106, which is an inverting Schmitt trigger. And the way that works is a Schmitt trigger inverter is basically an inverter that has different reference voltages for when it inverts and when it goes back to 0. So in this case, since we use a 12-volt VCC and ground, it divides it into thirds, and at 8 volts is the upper threshold, and at 4 volts in the lower threshold. And so what happens is when you first turn on power to the chip, which has 6 of these inverters on it, this voltage at this point is a 0 volts. And so the Schmitt trigger senses that since it's below the lower threshold, it inverts that and puts out 12 volts. And when it puts out 12 volts, that goes through this resistor and charges the capacitor. The capacitor gets charged instantly. Instantly, this swings up to 12 volts. And what happens is now when this reaches 8 volts, which is the upper threshold voltage, now this senses that a 1 or an on here, and it turns it off, and it goes down to the output of this becomes 0 volts. And since the output is now 0 volts, now the capacitor discharges through this resistor, but it discharges through the resistor a little slower. And so what happens is once it discharges through this resistor, it goes to, once it reaches the 4 volt range, then it goes down to, this senses a 0 again, and basically turns on, goes up to 12 volts again. And this way you get a square wave that oscillates at a frequency set by the resistor and capacitor values. So it's literally, the frequency is 1.5 over RC. And that's it. And sometimes you have to play around with the values. So for this inverting Schmitt trigger oscillator bank, we use 4 of these with various values of R and C to create these frequencies for the discordant metallic sound of the cymbal. So the key first step in constructing a cymbal circuit is to get a mix of discordant oscillators. So the Boss DR110 cymbal design incorporates 5 different oscillators. So basically we're using inverting Schmitt triggers here, and these are set at the frequencies that you can see here: 465 hertz, 317 hertz, 820 hertz, and 100 or 1.15 kilohertz, plus the white noise circuit that I showed you how to make from that transistor in a previous video. And the inverting Schmitt triggers basically oscillate spontaneously when you put them when you put the chip to power. I used a CD40106 integrated circuit, and I have different capacitor and resistor values written here. The way the circuit is designed by the Boss DR110 uses a more complicated way of generating these frequencies, but I sort of played around with it until I was able to generate the frequencies. Once the frequencies are made, then we combine them together in this passive mixing circuit where the white noise comes in at a higher resistance, so there's less of it, and the rest of it comes in through 100K resistors, and then there's a voltage divider to divide the signal down. Following this, we send part of the signal through a small capacitor into what we call a high filter. This is basically an op amp that's set up as a bridge T network to provide a resonant high pass filter that resonates. And we have one that resonates at a much higher level. This lets out the loud, high, hissy, white noise circuit with the ping that you want at the beginning part of the cymbal sound, and then the cymbal body, which is the metallic background sound resonates at a lower frequency. And this is divided down to swing around the 6-volt level through this voltage divider, and I'll show you how that works in practice. So these are the beginnings of a cymbal. Starts out with 4 discordant voices. Let's hear them and see them. Here's one. Oops, that one. That's one. That's 2. That's 3. That's 4. And the last one is the white noise. Time to bring them all together and create the basic foundation of a cymbal. So when you put all the different dissonant frequencies of the oscillators together with white noise at a ratio, you get the following sound. And that's what it looks like. You get each one. Here's the noise. That's noise. And we're going to turn that into metallic noise by putting it through some bandpass filtering that are resonant. Thanks for watching. So here is the discordant oscillators now connected to resonant bandpass filters. And so there's a high one and a low one. And so the low one is on the right there with the yellow capacitors, and the high one is the blue one. And let's hear what they sound like. So here is the high one. I'm gonna attach it right there. And that's what it looks like. It's got a little hiss to it. And here's the low one. So that's the cymbal body, and this is the cymbal ping. Sounds good. On to the VCAs and envelope generators. So now we have the cymbal mix of the discordant sounds and the white noise mixed up, going through 2 resonant filters here and an op amp configuration by a bridge T network. And here are the sounds. It's now on a perf board. Here is the low one. And here's the high with the hiss from the white noise in there. And it's time for the envelope generators and the voltage controlled amplifier. So this is the seemingly complicated envelope generator and VCA circuit for the cymbal voice of the Boss DR110 drum machine. And at first it looks very intimidating, but this could be divided and analyzed fairly simply. So if you look at my old video explaining envelopes and VCAs, basically the purpose of an envelope is as follows. Basically, this is a very simple envelope that I used for the snare drum and hi-hat circuit. It's basically you trigger it and you create a, you put it through a capacitor, which gives you a high pulse and a low pulse. You put a diode to ground to get rid of the negative voltage of it. And then you have a capacitor that charges and holds voltage, and then it decays slowly through, the voltage decays slowly through a resistor. And based on the decay potentiometer in this case, it creates an envelope that is either very short or very long. And that goes through a resistor, and that gets output to a voltage-controlled amplifier. So a voltage-controlled amplifier, put simply, is basically whatever voltage that's put in through this envelope is modifying the volume of the sound that's coming out to the output. So you have whatever sound you're generating going in to the circuit. In this case, it's white noise here. That gets put through a capacitor, and this is a swing type voltage controlled amplifier that's very common in both the Roland TR-808 and in the Boss DR110 circuits. And the way this works is it uses a single transistor. The transistor is biased to VCC. You throw a 1 mega ohm resistor. And what happens is any signal that's coming in over here, it's any audio signal, is basically getting amplified up here and going to the output. That amplification is being controlled by the voltage. That voltage is coming from the envelope generator. So the signal is really loud at the beginning of the envelope, and it becomes quieter at the end of the envelope. And all you have to do is modify the envelope and then stick that to the collector side of the transistor. Now, the big question is, why this diode? Well, so let's say the voltage in here is 0. If the voltage in on this part is 0, there's still going to be signal coming in over here, and so that signal will conduct through and can be audible. And you want it to be completely blocked if there's no voltage coming in, if there's no trigger input from the envelope generator. And so when the envelope, depends on what the envelope shape looks like. Once you shape the envelope using various resistors and potentiometers and things like that, that goes to the collector side of the voltage controlled amplifier, and the output is, and it's going through a capacitor here in order to get rid of the DC offset, and that is going to be the same signal that's coming in here, shaped to the envelope, so superimposed with the envelope shape, and that's going to be your output signal. So for the cymbal, it becomes a little bit more complicated. Let me show you what the design. This is basically reverse engineered from the schematic of a of the Boss DR110 cymbal voice. So you have a trigger that comes in here, right? This is the one that we're gonna take with our gate to trigger converter, and which I will show. And so it goes into two places. The first, it gets divided because we're going to be dividing into a cymbal ping and a cymbal body. So we have those sounds already made based on our oscillators, and so this is where those sounds are getting input. They're getting input to these two VCAs, one separate VCA for the cymbal body and one separate VCA for the cymbal ping. And these are constructed the exact same way. It's a single transistor going to ground, NPN transistor, with the diode here, and this is the output of it in the collector. The input of it is coming in from the envelope generator. So here's where the first envelope comes in, right, for the cymbal ping. Let's just look at the top part of the circuit. The first part of the circuit is an envelope generator that provides a very short decay, a 60 millisecond decay. If you look at these, if you look at this combination of resistor and capacitor, right? It's a low pass filter here. And it provides a very short 60 millisecond delay. And it gets mixed in with something here. This 10K resistor and this 100K resistor are basically functioning like a voltage divider, where the signal coming in from this part is going to be 10 times higher. The voltage is going to be 10 times higher than the voltage coming from this part. And what is this? This is coming from a transistor set up as an NPN transistor set up as an emitter follower. This is a standard NPN transistor that's buffering. And what it's doing is the other part of this trigger goes through a diode to prevent any negative voltages coming in there. And this is providing a 900 millisecond delay. The 1 microfarad capacitor and a very large resistor here, a 680 kilo ohm resistor. And what that does is it provides a much more delayed envelope, and that goes through the buffer. So the delayed envelope is divided down 10 times by this voltage divider, and providing the voltage control for this voltage controlled amplifier for the cymbal ping, the initial high ping sound. That output is then put through another high pass filter here, and this is another type of high pass filter. Is biased, to half the voltage here, and it's basically the same high pass filter that is used in the DR110 for their hi-hat cymbal, for their hi-hat signal. And once that's done, the output goes through this little tiny capacitor. It's a 2.2 nanofarad capacitor. That 2.2 nanofarad capacitor gets rid of all the DC offset, and so provides you a clear AC signal. That AC signal is now mixed in. This is a passive mixer circuit. This is a 5K6 resistor, and that's going to the output. The remaining part of the signal of the cymbal is going through a 10K resistor here. So it's being mixed in here together, and that's the output you get from the amplifier. That's the final cymbal sound. So now let's see how they do the cymbal body. So the cymbal body voice is down here, right? The cymbal body voice is going through a very small capacitor, or a 47 nanofarad capacitor, not that small. And here's its VCA, right? So it's going into the base of this transistor, and this signal is what's going to get amplified out here at the collector side, right? It has this diode that prevents, when this voltage is 0, it prevents any of the sound from coming in and going this way. So this is getting amplified here by this transistor, and it's based on the voltage of the envelope set by this circuitry here. So here's your first part of the envelope. This is a long 900 millisecond decay. And so it goes through this transistor buffer that we looked at before. That buffered transistor, basically, the first part of that signal is sent up and gets mixed in with the envelope of the cymbal ping sound that we discussed before. And then it also connects to a separate VCA for the cymbal body. And you can see here, there's another more of a delay in the circuit, like another decay side, which is another low pass filter here, 33K resistor, and a capacitor to ground. This is an electrolytic capacitor, so it stores the charge of the voltage, and then it slowly comes out through this 33K resistor, and now we are controlling this VCA for the cymbal body, which is a much longer delayed signal. That, once it comes out of this, comes out a little chunky sounding, so it's put through a very high pass filter here. It's a 470 picofarad capacitor and a 68K resistor here. So it's a very high frequency cutoff. And then once it comes out of that capacitor, it goes through another 470 picofarad capacitor, which is basically taking care of all the DC offsets from this. And then it gets mixed in with this resistor, and approximately a 2-to-1 ping to body ratio, because there's less resistance here and there's approximately double that resistance here. And that passive mix gets output to the amplifier. So at first, this looks like a very complicated circuit, but in the end, you could look at all the different components, and it's controlled by 2 separate VCAs, one for each portion of the cymbal. The cymbal body lasts a little longer. The cymbal ping is a very short envelope. So when you look at these two envelopes together, you see, let me just scroll over to this part here, and this is essentially what you get with a ping envelope and a body envelope. And when you look at the total signal, it looks kind of like that, where there's definitely a transition point in the envelope from here to there. And the initial part has more of the ping to it, and the latter part has more of the body in it, the metallic ringing, plus a little bit of that hiss from the white noise generator. So to make a complicated circuit simple, this is basically how it works. And it's basically the same thing, just a little bit adding a few more high-pass filters at the end here for both of the sides of the circuit, and just 2 VCAs, one for each element of the cymbal voice. And the envelopes are manipulated in standard fashion using just RC delay circuits. So resistor capacitors arranged in different values as high pass and as low pass filters to provide some decay and shaping of that envelope generator, to generate an envelope, which is basically voltage, a graph of the voltage over time. And that voltage goes to the voltage controlled of the voltage controlled amplifier to amplify the signal. So now let's put it in practice, and you can see what the envelope looks like on the actual circuit. So this is what our envelope looks like for the actual signal. You can see here that you have this initial spike with the trigger, and the spike has a very fast decay. And then you have the secondary envelope generator, which is for the cymbal body. So the initial one is for the cymbal ping, the initial high sound with the hiss, and then the cymbal body has the long, prolonged decay of the sound. And so those two envelopes are sort of superimposed upon each other, and those connect to the various VCAs of the circuit. So this is now the VCA and envelopes of the cymbal. It's a discordant bunch of frequencies plus a noise frequency, and combined with these envelopes, and you trigger it. I haven't constructed a trigger yet, but I will. But that's the sound it makes. And that's the cymbal sound. And you can see the envelope here. I have it taken off of the cymbal body envelope, which is a long delay one. And you can see it on this when I make the sound. And all I'm doing is just basically touching it to the LFO, just for a short, trying to get a short trigger. And you can see the prolonged delay. This is, divisions here are 100 milliseconds, so you can see it goes fairly extensively. Let me change the division length here, make it 200 milliseconds. So you can see the whole wave. Let's drop it down. Here we go. So I stopped it. You can count the squares. 1, 2, 3, 4, 5, 6, 7, 8. Basically 8 squares, so that's 1.6 milliseconds of decay time for a typical cymbal, which is actually fairly spot on. I tried some cymbals out and it actually sounds pretty realistic. I just have to get make a gate to trigger converter, and that will basically make this circuit complete. Here I have the symbols on the symbol on the perf board. I just have to make this is the two envelope generators, plus for the high part of the for the metallic part of the cymbal, plus the noise part of the cymbal, and the body part of the cymbal, and includes the hiss at the end. So stay tuned. I will make a final one and put it with the LFO. Thanks for watching.